Hello everyone, my name is Ho-Ren from Virginia Tech. You can call me Jack. This is a joy work with my colleagues and my advisor at Virginia Tech and RWTH Aachen. Processor designers are facing hardware limitations such as the slowdown of Moore's law. Meanwhile, global data volume increases significantly and it will keep increasing as well. To continue scaling performance, recently there is an interest in coupling systems with non-cache-coherent domains. These systems have multiple cache-coherent domains wherein each domain has hardware-supported cache coherency, but no inter-domain cache coherency. In shared memory or symmetric multiprocessor SMP systems, cache is an essential element for shared memory. If there is no cache coherency, the data correctness in such systems is not guaranteed. Systems with non-cache coherent domains are usually heterogeneous. Examples range from mobile devices to clusters. Plus, recent market trends also show that high-end servers with different ISS such as ARM and PowerPC are pushing into data centers. Using these emerging systems brings power efficiency and performance benefits. However, developing applications for such architectures is difficult. Distributed shared memory (DSM) is one of the solutions to this problem. DSM provides programmers with the illusion of a single address space across multiple domains, also called nodes, each of which has its own memory, often cache coherent. This allows SMP programming frameworks such as Intel Silk and OpenMP to view the multiple domains as a shared memory SMP system and use the CPU cores of the different domains for data parallel and task parallel computations as if the cores belongs to a single coherent domain. We define programmability as the additional programming effort required to run existing shared memory applications in newer distributed architectures. The more programming efforts is required, the lower programmability it is. Previous works usually use sequential memory consistency (SC) as their DSM protocol, which is an validation-based multiple reader and the single writer protocol. It is the gold standard among DSM models. However, we found several bottlenecks in previous works, such as significant numbers of write invalidation messages, forced page sharing, large number of read page faults, and the large synchronization overhead. We envision in the near future heterogeneous domains like two domains will appear in data centers. The closest working prototype on real non-cache coherent domain is a x86 combination integrated via a high-speed interconnect. We experiment on this prototype to mimic the envisioned future architecture. Our goal is to efficiently leverage existing programming frameworks while transparently scaling out a SMP application on multiple non-cache coherent domains. To achieve this, we adopt shared memory parallel programming models like OpenMP and Silk, which are mature and widespread. For example, in OpenMP, a work sharing region, also called parallel phase, can be split into two main components, parallel execution and synchronization barrier. This allows programmers to easily spawn multiple threads and distributed parallel work, which permits greater parallelism and higher performance. Inspired by such SMP operations that permit weaker memory consistency, we developed a DSM protocol called MWPF that trade-off memory consistency for higher performance in select SMP code regions and targeting heterogeneous ISA multiprocessor systems. Multiple writer MW protocol allows multiple writers from different nodes to write to the same page without coherency in a work sharing region. In this example, we focus on a single page case. The square represents the page. The page status can be either write exclusive in blue or read share in green. The white square means a snapshot of the page. The orange square means a diff page between the snapshot and the up-to-date page. In this example, node 1 is the default owner node. Both nodes have the page read only before entering the parallel phase. When the execution reaches to a parallel phase, it enters MW parallel phase. Say node 0 issues W2 generating the rifle. In this example, since node 0 is not the default owner node, it makes a copy of the page and changes the permission to be exclusive without cross-node coherency. W2 and the following writes, such as W5, will not incur page fault for the duration of the MW parallel phase. On the default owner node 1, W4 doesn't need to create a copy of the page. It directly gets the write permission and then write to the page without coherency. Same for W6. This saves the latency of sending invalidation messages and permission changes caused by different interleavings of writes like W2, W4, W5, or W6. Once the execution hits the synchronization point, it enters NW merging phase. In this example, both nodes write to the same page, so merging is required. Now, default owner node 0 creates a diff by applying an XOR operation between the original copy and the up-to-date version of the page. Then it transfers the diff to node 1, which merges the diff with its copy of the page. On the other hand, if the DSM finds there is only one node writing to the page, it doesn't need to perform merging for the page. After all invalidations and merges have been performed, the work share region ends, and the DSM transitions back to SC for the next serial phase. Because MW protocol may not pay off in all scenarios, we introduce a heuristic named smart regions to select the best consistency model for a given work share region. Also, we provide a providing and prefetching mechanism to further reduce the number of repage faults in work share regions. Last but not least, we design a low overhead multi-domain synchronization primitive for avoiding redundant page transfers caused by DSM. More details for these designs can be found in the paper. We modified the Popcorn Linux project OpenMP runtime to integrate our proposed primitives. Popcorn's OpenMP runtime provides the ability to migrate threads executing in a parallel region between nodes to take advantage of remote computing resources. Our modifications to the runtime only added 98 and removed 3 lines of code. This shows the applicability of our design. We experiment on an x86 ARM combination with 16 and 96 cores separately, integrated via a high-speed interconnect to mimic the envisioned future heterogeneous domain architectures. In our experiment, we always use all computing resources in the system. The benchmarks we have used are mostly from HPC settings, including Parsec, NPB, Phoenix, Rodinia. This slide shows the details. We present the result of each application as a small plot from A to I. In each plot, different colored bars on x-axis show speed up or for x86, ARM, SC, MW No Smart, MW, and LPF. The speed ups are normalized to a single node execution time on x86 on y-axis. The higher the better. Compared to the baseline SC, our MWPF's average speedup over 9 applications is 11% and up to 33% for SP. Additional results are in the paper. To conclude, MWPF achieves on average 11% speedup. It means we can improve performance in non-cache-coherent domains while enabling legacy SMP applications. Our code is open source and available on Popcorn website.
Mike Factor asks, first he thinks it's a very interesting talk, which I do as well. He wants to know, how do you handle conflicting updates by different nodes during the merge phase? So if there's a conflict in the merge phase, what do you do with that?
So basically, that's actually what the merging phase does. So if you check the merging phase, right, it actually solves those kind of conflictions. And the reason why I think probably you would be interested is that how about actually multiple nodes writing to the same variable? So in this case, this is not actually allowed in the work sharing region, because this has been actually defined in this kind of shared memory programming model. So in our case, we only have to deal with the case where multiple nodes are writing to different variables but sitting on the same page.
And Let's see. Sakiberg asks, sort of related to that, but what is the percent difference in the total number of memory accesses, including the exclusive ORing? So you do actually more memory accesses during the merge. So how much more is that work is that?
I didn't actually take this number, so it's hard for me to actually answer this one.
So
But yeah.
the shorter question though is, how long does the merge phase take per page? You know?
Yeah, I didn't actually measure this latency, but I can tell you the upside for this phase is basically when you are actually in the ender phase, right? You don't need to actually send any invalidations, and this can be actually quite, brings you a lot of overhead. Yes, and you just have to merge it one shot. That's it. In the end.
And if you were, if you could change the page, if you could dynamically change the page size or decide beforehand what size pages one wanted, would that make a, for the shared region, would that make a big difference?
Could you repeat the question?
So
again?
do I presume that you assume that there's a single fixed page size for the DSM.
Yes. Yes.
If you could make that page size bigger or smaller, would that change very much?
In terms of what?
Would it be faster or slower? Would the merge be, I presume there'd be more conflicts if the pages were bigger, but it might take you less time to merge them.
To merge them, you just need to send, so the overhead I can tell you is just one, the snapshot of the page, and then you need to actually send this div to the remote node and then perform the XOR. And then other than that, if let's say the size is different, then of course this duration has to actually, be longer.
Right.
Yeah, but if you consider
that as much overhead, it'll be an interesting trade-off.
Right. But the same actually for the sequential consistency, because once you invaded the page, the next time you need to bring the entire page. So
right. That's right. Yeah. That's why it's hard to figure that out from the chair.
Right.
Let me ask one last question because we're running short on time. This is from Wei Wen Wang from the University of Georgia. Do you need to modify the application source code? If not, what is the instruction set of the original binary? Also, how do you mitigate the false sharing issue? So I guess there's two questions.
Yeah, so the first question is, do I need to modify the application source code? No. So we only modify the runtime. So it's like one-shot modification. So once the runtime has been modified, and then you just need to compile the applications. So recompile your application, then you can just enjoy all the benefits that I have mentioned in the presentation. Yes. And what's the second one again? Sorry.
How do you mitigate the false sharing issue?
Yeah, so for false sharing, again, false sharing is actually caused by many nodes that actually write into different variables, but they are actually on the same page. So in this case, we actually provide this multiple writer protocol, right? So that means multiple nodes can actually write to the page without synchronization, without coherency. So there is no actually, so-called false sharing in our region, but we need to do the merge. That's our overhead in the end. Yes.
Okay, great. Thanks again.
No problem.
Thank you again. Good talk.